Hello everybody. Once again I'm here. I'm Mr. Steele. Well, depending on who's watching this, you probably already know that. But at the same time, just in case, I'll introduce myself. I've taken a couple days off from doing the BC lessons just to kind of get myself some time to kind of process everything, think about all the new developments in the district, and to do a few summer work videos for the incoming AB students that are going to have some interruptions to their learning. Which means it's been a few days for me. It might not be for you. You might be watching these at a different time and jumping right into these. You might have just watched a previous one. So in any event, if you haven't for a while, welcome back. It's good to not see you again, although I'd rather see you. I don't know how to say that. I can't say it's good to see you again because I can't see you. Like if I close my eyes, it's good to see you. Okay, whatever. In any event, this is going to be the beginning of the final full kind of comprehensive unit of Calculus BC. At least with the structure that I teach it. There is an extra lesson at the end, but for the most part we've covered every single topic that's out there once we complete this small unit focused on this idea called Taylor Polynomials. So as we prepare to jump into it, I'm going to start in kind of a different place. I'm not going to write anything down, although in a little bit I'll start to, and I'll do a full derivation to show you where they came from. I'll do a couple examples with you, kind of giving you all sorts of angles and looks at it. And then in this particular lesson, there's really only one topic. We're really doing one thing today. So I'll end up closing this lesson off with the triad at the end. So it's going to be slightly structured differently than the ones on series convergence were or any of the previous unit were. But I think you'll find it just as beneficial, and it'll be structured and delivered in the same way for the most part, just not with all the extra triads in the middle. Now, before we start to talk about Taylor polynomials, it'd be worth doing two things. And if you disagree, well, that's too bad. You can't argue with me because I'm the person that's here doing this. So the first thing I want to point out to you is although you may not know what a Taylor polynomial is, you may think to yourself, what in the heck is that? I've never done that before. The truth is you have actually dealt with a very simple Taylor polynomial in the past. So let me write something down for you here first, just as kind of a quick introduction. So as I finish writing this expression, my question to you would be this. What is that I just wrote? Speak up, I can't hear you. Oh, yeah, that's right. You're probably going to say this is a line. Like it is, in fact, just a line. If you said it's a tangent line, well, yeah, it could be. That'd be perfectly fine to say. But it's not necessarily implicit or just always. It's not inherently, there's the word I'm looking for. It's not inherently a tangent line. It's just the equation of a line. It passes through the point x sub 1, y sub 1, and it has slope m. Now, having said that, there are a couple different notations that could actually rewrite this in a slightly different way. So let me introduce you to the method through which I was taught the equation of a tangent line. So I was taught this, that y is equal to f of c plus f prime of c times quantity x minus c. Now the reason I bring this up is that in truth this isn't any different than the equation on the left. Okay, fine, that's a lie. It looks different, but it has the exact same components. So specifically we have this, f of c is y sub 1, that's just our y value at x equals c. C, hopefully you too can see, is x sub 1. And then last but not least, if we want to know the slope at a particular point, that would be the derivative at x equals c, which is f prime of c. So in truth, this thing over on the right side is exactly equivalent to the thing on the left. The reason I bring that up is because oftentimes students, when asked, will say that this is a tangent line, which again, we talked about how it's really just a line, but for the moment I can buy what they're saying. They'll say this is a tangent line, but in truth over here, they might not necessarily think about this in the exact same way, even though it is a tangent line. In addition, though, to being a tangent line, this is also what's called the first Taylor polynomial. So in a sense, these two things have this thing that we call the tangent line equation actually has kind of a dual meaning. It also is, for some reason, this thing called a Taylor polynomial, and somehow it's the first one, not the second, not the 0th, but the first. So what I want to do is I want us to actually figure out today what a Taylor polynomial is, how it connects to tangent lines, of course, but also other degree functions, and I want us to be able to generate a Taylor polynomial as well as its corresponding subtype, I want to say subset, a Maclaurin polynomial, or a Maclaurin polynomial if I try to talk like Scrooge McDuck. So that's a really simple goal. It's a very finite goal. I'll try to give you some insight about what things mean also as we go through. You'll see when we get there. But for now, I just want to ground this in the idea that really this is just like a tangent line. It's just going to have more in there. We're not just talking about lines. We're talking about polynomials. Now, in addition to that, before we dig in and I start to get you there, I created something a few years ago, I think first in 2015, so I guess it would be, what, like 5 years ago at this point? I created a demonstration on Desmos that I thought did a good job of illustrating the concept of these things called Taylor polynomials. I'm going to show that to you now. Obviously, it's not going to be the same interactivity, so I'll just pretend that someone's here with me as I do this activity. So what I'm going to do here is I'm going to graph a couple functions. I'm sure you've seen these functions before. I'll graph f of x. So take a look at that function right there. Take a look at it. Look at it nicely. Take a look. What function do you think that looks like? Like, what function do you think this is? Go ahead. Call out your answers. I hear someone saying sine of x. Yeah, that looks a lot like sine of x. That sounds good. We're thinking sine of x is probably f of x. This black function is sine of x. Cool. Good job. We're doing great so far. What about g of x? What do you see with g of x here? And yeah, that is starting at 0, 1. Yeah, you think it looks like cosine? This is so weird to be pretending someone's talking to me. I guess it's like having an imaginary friend. Ah. Yeah, if you said cosine, it makes sense. It looks an awful lot like cosine. Yeah, I'm seeing it. Look at that. It's minimums down there at pi. Like, look at that. That looks like cosine. So we said f was sine, g was cosine. Let's look at one more. So this one may be a little bit harder to look at, but do we have any thoughts about what function this is? Like, yeah, you think e to the x maybe? I mean, it could theoretically be 2 to the x or something, but e to the x would be a reasonable guess. Like, that looks pretty reasonable. Let's see. That's 0, 1. Let's see where it is at 1. There's 1. Do we see 2.71828? 1828 looks pretty darn good to me. Looks like we're pretty close to e. So yeah, I'm going to go ahead and venture to say that if you said e to the x, that seems like a pretty good guess. Now here's the thing. So you said sine of x, cosine of x, and e to the x. So if you said all of those things, guess what? You're wrong! Ha! Yeah, you're wrong completely. Totally wrong. Yeah, well, you fell right into my trap. So look at that. You're like, it's sine of x, totally sine of x. What? Yeah, it stopped being sine of x. Okay, so that one wasn't sine of x. G of x, the cosine. Surely that can't also be oh. Yeah. Not cosine. And then last, but certainly not least, put an e in there, that's fine. There's e to the x, right? Definitely e to the x. Oh, yeah, no, it's not. It's not e to the x. Yeah, it turns out none of these things are what you expect them to be. In fact, although they look really good, in fact, you might even say they look like, especially zoomed in a little bit, it looks like they converge to those three functions. The truth is they aren't. They aren't the same. Each one of these is actually a polynomial, not the transcendental function that we were just analyzing. So keep that in mind. Like, that's kind of an interesting place to start. Now, having said that, I want to explore that thing I was just describing to you a little bit. So what I want to do is I want to show you these things in action. So right here, this is no lie. This is sine of x. We're looking at sine of x. Right here, so let me move this back. We're now going to look at the graph of what's called the Taylor polynomial for sine of x, centered at x equals 0. One might also call this the Maclaurin polynomial for sine of x, which we'll talk about the difference in just a second. So what I'm going to do is I'm going to slowly add terms to this polynomial. It starts with just a single term. I think in this case it actually starts with 2 terms, and then it slowly adds more and more terms. So watch it in action. Watch what happens. Okay, so as this is happening here, I hope that you can kind of see that it looks like the green one, which is the polynomial one, looks like it's ha, 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 ha. It's like it's doing cross country or something. What's happening is as it moves forward, it's slowly stitching itself to more and more of the sine curve, which is kind of an interesting idea, until we reach this point at the very end, which is coincidentally 42 terms, where it's got a lot of the sine function there. It looks like it's doing a really good job. If we wanted to stitch or add more and more terms, if we wanted to add higher and higher degree terms for this polynomial, we'd keep getting more and more of this sine curve. So that was sine of x. Let's take a look next at cosine of x. We also had one that looked like that, kind of an imposter cosine. So there it starts. Look at that. Notice it's an even function every time. It's a parabola, or sorry, it's a bowl every single time using Franklin words. It's a bowl. It just keeps stitching itself to the cosine curve. Every term adds a little bit more accuracy, a little deeper or wider accuracy, until we finally get to 42 terms, where I stop just for the sake of stopping. So look at that. If we zoom in, look at these things. There's not even a difference there. These look like identical twins. Like, yeah, the color's changing. It's kind of Clemson colors, it looks like. But those are identical. They're doing the exact same thing that whole time. The only difference is, of course, one is slowly adding more and more terms to the other and making it closer and closer. It's like you could say the purple one is converging to the orange one. Last but not least, let's look at e to the x, because I said that one is in there. So here's the e to the x one. Now, it's kind of hard to see here, but if you're looking on the left side of your screen, it should look like there's just like, it just keeps stretching further and further out. It's moving further and further, stitching more and more to the original e to the x curve, slowly, like making them look almost identical. And of course, as we get there, they are not identical. You can see that it stops. But once again, if we just kept stitching more and more terms on there, we'd get exactly what we wanted, which was a perfect representation of e to the x. In fact, all of these functions, its name's not going to mean a lot right now, but all of these functions will if you were to add up all infinity terms of this polynomial. As in, if you were somehow able to capture an infinite number of terms of this polynomial, generating them with a particular pattern, you could actually get the entire thing. All three of these functions have what's called an infinite interval of convergence, meaning that they will converge to the entire function if you just add enough terms to get there. So now, having said that, like, that is my best description for what these what these Taylor polynomials are going to do. They're slowly going to find a way to match more and more behavior of a function over time as we add more and more terms to that polynomial and let their degree increase. So our job today is to figure out not necessarily how I did this exact thing, although it's not actually difficult to figure out, especially if you look on the left side. There's something to do with series that we'll connect in tomorrow. But for the moment, our goal is to be able to generate one of these. Not 42 terms, because that would be ludicrous. Our goal is to generate a handful of terms, maybe 5, 6, 7 terms, just so we get comfortable with the pattern and how these things are connected. So that is my demonstration of what a Taylor polynomial is. It's some new version that you can use the original function to generate. It's going to connect to the original, to another function, and it's slowly going to replicate or create kind of an imposter of the function that's a polynomial, rather than an actual complicated, transcendental, or complex function. So having said all that, let me point out that what we're about to do is I'm going to now derive. Like, I'm going to take some known results, some things that we know how to do, and I'm going to work my way through and show you where the Taylor polynomial comes from. That's going to take a little bit of time. Think of this like a proof, but it's not a proof in the traditional sense where I'm just like giving you a formal explanation. I'm literally just developing the idea and showing you how it connects to things you know how to do. In particular, plug in function values and differentiate functions. So I think this is a valuable use of a few minutes. It's probably going to take me about 4 minutes to work through, lots of little nitty-gritty writing. But I do think it pays off in the end. If I just give you a formula, you're just memorizing a formula. I'd rather you see where these pieces come from, because I think it works a little more authentically. And my class has been very successful on this test for the last few years, so I think it'll pay off. Now, having said that, as we go to derive where the Taylor polynomial expression is going to come from, how we would get one for a function f of x, we're going to start by assigning that very function that we want to look at. So I'm going to ask you at the very start of this derivation to consider some function f of x at x equals c. So in other words, there's a point on the function f of x that has coordinates c comma f of c. And again, notice that that kind of matches what we have up there. That's x sub 1 and y sub 1 the same way as before. So that's an important starting spot. Now what we want, like, this is a little bit complicated the first time you see it. So this is kind of the, like, okay, you can kind of see what it looks like, but the question of what is it that we're trying to do here, that we're going to derive in just a second. The thing that we want is we want to develop a polynomial. So first and foremost, it's a Taylor polynomial, meaning it's going to have a bunch of terms that have whole number degrees, like all that good stuff. But we want to develop a polynomial that matches something about another function. So, and I got to do this a little carefully. I have trouble having to write at the same time as like longer stuff. So we want a polynomial that matches every derivative of f of x. So in other words, the process we're going to use here in just a second, derivative, is going to be differentiation. And specifically, it's not just every derivative of any function in the world. It's going to be specifically the derivatives of f of x, and specifically those derivatives evaluated at x equals c. In fact, if you're wondering why it is that we choose the letter C to represent this value, there's lots of reasons, but typically C in this context of Taylor and eventually Maclaurin polynomials is standing for center. It's going to be the center of this polynomial that we construct. Could also do, I guess, C for construct, or C for C's candy. Oh, that tastes good. But your call. So there's where we're beginning. That's our goal. That's what we're going to try to accomplish, and we're going to jump in. And now, as I said, I'm going to try to develop this idea for you as we work our way through. I don't have the ability to answer your questions as I do this. That would be kind of cool, but that's not the ideal way to let people work on their own pace. So here's where we go. I'm just going to start working through it. Of course, pause the video if you need to. Let me know if you have questions. I'll try to help out. So starting things off, I'm going to start off with fulfilling this wish. I want a polynomial that matches every derivative of f of x. You know what? To start things off, I'm not even going to think about it in that way. I want a polynomial that matches and is equal to f of x. I'm just going to assume that's the case at the very beginning. I want to transform, there's a great word for it. I want to transform f of x into a polynomial. Well, I don't know how to do that. Well, I do, but you don't know yet. Collectively, we do not know how to do that yet. So what I'm going to do instead is I'm just going to start by writing out a general polynomial. I'll write out a general polynomial that has a constant of a sub 0. So I'm going to use little subscripts to indicate which degree term I'm looking at. Then we'll have a first degree coefficient times x minus c. Let's make sure I do this correctly. Yes, there it is. Okay, times x minus c. And again, the reason why, by the way, if you're not sure why I have that x minus c, is to center it at c, to make sure when we plug in c, we just get a of 0. But there it is. I'm just kind of using that tangent line. Like right now, in fact, it is a tangent line. Then from there, I want to figure out the coefficient of the second degree term. And it's going to have x minus c to the second power. And then I'll figure out the third degree term, which is x minus c to the third times some coefficient a sub 3. And then I'll have the fourth degree term that you can kind of get the pattern by here. So again, what we're doing is we're making sure that it matches every single time all the way through. So there is our first step. That is f of x as a polynomial. So we've transformed f of x into a polynomial. Now having said that though, we don't want it doesn't necessarily need to match everywhere. We say we want to match every derivative at x equals c. So specifically what we really want is we want to plug in some value x equals c. So in here, let's imagine and see what happens if we do. Hopefully we'll get some valuable relationship out of this. Well, as soon as we plug it in, we get, oh, wait a second. I forgot. You aren't trying to copy this down at the same time I am, so I can totally cheat on this. Oh my gosh, I think my world just got better. Look at this. Let's use bright candy red at this point. So we're going to do f of c. So that means everywhere I had an x, I need to plug in a c. I think there's probably a joke about air conditioning because I just said plug in AC, but you know, it's not funny enough. So there it is. So we've just plugged in C. Now the question for me, or that I want to ask you, is can you see what just happened? Well, anywhere where there was a C plugged in for X left us a factor of C minus C, which is just 0. So that term went to 0, that one went to 0, that one went to 0, that one went to 0. In fact, every one afterwards went to 0, which just means f of C is equal to a sub 0. So what we've just determined is one of those coefficients, or in this case a constant, that we need in order to make this thing work out. So pretty powerful stuff. So let's see. So that's my first move. So I'm starting there. The next thing I'm going to do, though, is I'm going to attempt to figure out what the next term's going to be. I'm going to slowly work my way through here and keep matching up derivatives and values of f of x with this polynomial. Because again, our theory is if it's going to be equal to a polynomial or it's going to match, we want to just represent that polynomial as easily as we can. So I'm going to make my move next. So we just looked at f of x, we figured out what f of c was. The next thing I want to do is I want to figure out what is f prime of x going to be equal to in this case. So if I want to find f prime of x, of course, that's going to be equal to the derivative of this polynomial, because we just said in the beginning that these two things are equivalent to one another. We're trying to present the idea that they're the same. So having done that, when we take the derivative of the polynomial up there for f of x, which is right here, this is what we're differentiating, where the green arrow is. Green arrow? No, it's green lantern. Never mind, different. So the derivative of a sub 0, which is a constant, is just 0. The next term, though, has a sub 1 times x minus c. Well, that's like having it to the first power And if you take the derivative of an x to the first power, you just get 1. Like, that's just the power that's right there. So in fact, let's make sure I do this correctly. In fact, many people would just simply write a sub 1. But for the sake of developing a pattern, if you will, I'm going to imagine we bring down the 1 and then subtract the 1 by 1. So in a sense, this is what I'd rather see. This is going to be 1 times a sub 1. And then, of course, that whole thing would be x minus c to the 0 power. For the next term, we'll bring down the 2. That's just the power rule, right? X to the n's derivative is n x to the n minus 1. This will be 2a sub 2 times x minus c to the first. Then it'll be 3a sub 3 times x minus c to the second. And then 4a sub 4 times x minus c to the third. And you can imagine if we kept going and we wanted to see more terms, we could absolutely do that, but we're just not going to at this point. So there is f prime of x. Our next move, just like before, is that we don't need every derivative to match. We want every derivative at x equals c to match. So what I'm going to do is I'm going to replace all the x's with a c. And as happened before, you can probably predict what's going to happen here. We're going to get a ton of zeros. Lots of things are going to zero out. Now, I should have pointed something out here. This first one that I replaced, I probably should have just eliminated it because its derivative was 1 anyway. That was just a constant. So I'll just eliminate that right now. Instead, I'll point out that every other term is going to go to 0, which means just like we did on the previous one, what we just found out is that f prime of c is going to be equal to 1 times a sub 1. Now I can feel through this digital camera, I can feel that many of you are like, why don't we just call it a sub 1? Patient young Padawans. We shall reveal that in due time. So there it is. We've done f of x and f prime of x. What do you think's coming next? If you guessed second derivative, you're right. Come on down. So in this case, let's look at the second derivative. So once again, all I'm doing is I'm just differentiating that previous one. So I'm going to look at this guy and differentiate it. Of course, that 0 is already gone. The next thing was a constant now too. So it's going to be 0 plus 0. For the next one, if we differentiate this term I just circled in blue, that's going to give us plus 2 times the 1 that's going to come down from the power rule times a sub 2. And then, of course, that's it, because x minus c's derivative is just 1, so we don't need to do anything on the back end. Then from there, for the next one, we'll bring down the 2. I'm just bringing down the power, and then power minus 1. So this will be 3 times 2 times a sub 3 times x minus c. The next one will be plus 4 times 3, a sub 4 times x minus c squared. And of course, we went to the next term. You can probably even predict what that next term would be. It'd be 5 times 4, a sub 5, x minus c to the third. So we got all that stuff. Why is this helpful? Well, as soon as we have it, we can plug in c, and then we can see what it is that happens. Like, what is the relationship we end up with here? So plugging in the c value a couple times, that leaves us with f double prime of c being equal to, well, we've got a 0, a 0. Everything afterwards is going to be 0 too, obviously. All that we're left with is 2 times 1 times a sub 2. So we now have a relationship that involves that second degree coefficient. And by the way, I'll pause for a second. Like, you're probably watching this on super speed. I probably sound like a chipmunk as I'm talking really fast because you're moving really, really fast through this video. Take a moment to think about what is it that we're accomplishing here. What is it that's happened each time? Each time what I've gotten is a relationship that involves a derivative at a specific point on the graph of f of x and that coefficient. Because remember, our ultimate goal here was to figure out what is this polynomial right here. What is the polynomial that's going to give us that thing that slowly gets closer and closer to the function, that does a really good job of estimating. It does a good job of estimating, but a good job of impersonating the original function that behaves the same way. And so we're almost there. We found another coefficient. We've got another relationship here involving a sub 2. Next one to come should be a sub 3. So let's see. Let's go to another. So we're going to now take the derivative. Oops, wrong color. We're going to take the derivative of this one. It's going to be talking about f triple prime of x. Well, according to what we have here, that'll be 0 plus 0 plus 0. Then on this piece, when we take the derivative, of course there's a 1 there, so when we bring that down, we'll have 3 times 2 times 1 times a sub 3. The next one will be 4 times 3 times bring down the 2, a sub 4, x minus c. And for the sake of filling in space, we might as well put it in here too. If we went to one more term, we'd have 5 times 4 times 3 times a sub 5 times x minus c squared. And again, I'm probably going to run out of space because I think my head's right there, but it is what it is. Ha, I've got room now. Okay, having said that, we've done this trick a few times. I'm going to go ahead and borrow this a little bit. So there's our stuff. We once again want to plug in x equals c. So we'll replace all those x's with a nice red c. When we do, this leaves us with only a few terms left, at least the ones that we can see. Huh, the ones that we can see, huh? Yeah, I'm proud of that one. I didn't even expect to walk into that one. The one thing I did expect, though, is we do end up with f prime of c, or triple prime of c, being equal to 3 times 2 times 1 times a sub 3. Now, once we reach this point, I usually point out to people that the truth is you can probably predict what's coming next. In fact, I wouldn't even ask us to go a step further. Instead, I'd probably opt to do this instead. Pick another color. Ooh, let's pick a rich royal blue. Yeah. Oh, nice. What I'd probably say is, tell me this. What do you think the fourth derivative at c is going to be? Based on what you've so far seen on all of these problems. Let's see if I can get this right. So we've got f of c is a sub 0, f prime of c is 1 times a sub 1, f double prime of c is 2 times 1 times a sub 2, f triple prime of c is 3 times 2 times 1 times a sub 3. I'm hoping that your thought is this. It'll be 4 times 3 times 2 times 1 times a sub 4. And if that's what you were thinking, well, gosh darn it, you're right. That's absolutely what's going to happen. We have a pattern developing here. In fact, I would argue that we probably have a pattern that's already fully developed. We can see and predict what's going to happen for pretty much any term. Having said that, though, let's collect all this together and see if we can finally answer the question we were angling for at the very beginning. Let's go steal this down. Okay, so here's that polynomial that we were working on. Our goal was to figure out this polynomial. So in other words, what we wanted to determine were the values of these coefficients. In fact, I think I probably need to change that to purple, but either way, that was what our aim was. We wanted to figure out what was the polynomial that matches f of x at all its derivatives. So to get there, we brought a couple different things along. I'm going to go steal these back. There's one. There's another. Because again, the idea here is, can we use this information to then predict a way to generate this polynomial? Because our goal is to be able to actually compute these things. Okay, there we go. Alrighty, so after all of that, here's what we have. We have f of c equals a sub 0. In fact, I'll hold these back for a second. So f of c equals a sub 0, cool. What that means is that we can generate the first term of this thing called the Taylor polynomial. Instead of calling it f of x equals that, oh, I've got an idea. Let's do this. Hold on. Sorry, I'm thinking this through as I go. This is my one opportunity to not have to worry about time as I do this lesson. Because, of course, you can pause at any time. You can speed me up. God, that'd be a creepy world if you could, like, speed me up during class and, like, be kind of funny. Somehow I've highlighted that thing and I haven't yet gotten the color changed. There we go. Okay, so there's our polynomial. Here's what we're going to do. We're going to use each of these pieces of information and draw things out. So first and foremost, we said f of c is a sub 0. We're going to replace a sub 0 with f of c. Next, over here in green, here, let me pull it up here. Over here in green, we have f prime of c equals 1 times a sub 1. Now, truthfully, you could just go ahead and replace that as f prime of c if you wanted to, but I want to be more specific. I want to point out that this solves really cleanly to f prime of c over 1. The reason I want to point that out is not because I'm one of those people who doesn't want you to simplify, because truthfully, I'd probably enjoy having you simplify your answers, but it's because there's a pattern developing here, and I want you to see the pattern if you haven't yet. So let's go to the next one. F double prime of c equals 2 times 1 times a sub 2. That means that if we divide both sides by 2 times 1, we'll get a sub 2 is equal to f double prime of c divided by 2 times 1. Which means once again we can go fill in a factor, excuse me. F prime of c is equal to 2 times 1. For a sub 3, let's see what color we're going to have there. Oh, we had navy blue, I want to say. So a sub 3 is this guy right here. We are going to have, it looks like, a sub 3 is equal to f triple prime of c divided by 3 times 2 times 1. So 3 times 2 times 1 is going to go down in the denominator of this coefficient. By the way, that is what we're really doing right now. We're just generating the coefficients of this Taylor polynomial centered at c. Again, we'll give you names in a bit. Last but not least, we got one more coefficient that we can see in our polynomial. So we're going to get a sub 4 equal to, if we just divide by 4 times 3 times 2 times 1, we'll get the fourth derivative of c divided by 4 times 3 times 2 times 1. And it's at this point that you probably realize that this is really impractical to keep writing the massive product in the denominator, 4 times 3 times 2 times 1. And the answer is yeah, it is not practical at all. But at the same time, let me point something out. Like, guys, we did it. Like, we got it. Look at it. We did it. We found it. We now have a connection between these things. Oops, let's not quite get there. Like, we've done a lot of work. Let me insert a new page. Let's just go ahead and have a page to celebrate this. This thing is exactly what we were looking for. This is the polynomial that matches that other one, f of x, at every one of its derivatives. And in fact, if we continued forward, we could actually go and generate any term in this particular polynomial. Specifically, let me point out this. If we wanted to write what I'd call the general term here, that general term can be easily generated just as well as these ones did. Like following the patterns here, let me point something out. Do you know of some pattern that goes 1, 2 times 1, 3 times 2 times 1, 4 times 3 times 2 times 1, 5 times 4 times 3 times 2 times 1? And if you don't, let me just say, what? You should. That's not a triangle pointing at a ball. That's a factorial. This is really just a factorial pattern. It may not be immediately obvious, but this is, the first one was 1 factorial. The second one was 2 factorial. The third one is just 3 factorial. Oops. Third one is 3 factorial. The fourth one, that rich royal blue that I chose there, that one is 4 factorial. Basically, this is just a factorial pattern. And in fact, if you wanted to generate the nth degree term of this thing, you could do so very easily. It would be the nth derivative evaluated at c divided by n factorial, because notice how the factorial in the denominator matches the order of the derivative. And then last but not least, we'd multiply times x minus c to the n power. And then, of course, we'd have to add on because there would be terms later. Like there's an infinite number of terms here. But this thing is the Taylor polynomial. I should have had this massively written out ahead of time. It's the Taylor polynomial for f of x centered at x equals c. So now, let me first say this. Having done this one time, you'll never have to do this derivation again, ever, like at any point. Obviously, we'll differentiate and stuff, but you'll never have to do that massive set it equal to this polynomial, check term by term. That part's done. What we're going to do from now on is we'll go through it quickly and in a fast way so that you can see how this works out really nicely. So now, having said that, a couple things to point out. The one thing I do want to point out here more than anything else is that this expression thing that we're describing here, it's really all this work to figure out this coefficient. Like that's really all the work we were doing was trying to figure out how we can determine the coefficients for each term of this thing called a Taylor polynomial. So that is the coefficient we found. We found a generalized way. If we can just find the nth derivative, whatever order we want for that derivative, divide it by that order factorial, and then multiply by x minus c to the n, we get what we wanted. Having said that, there are a couple things that we want to point out that are a little bit different here. So first and foremost, there are two different types of things in this situation. A lot of people describe it as you have Taylor polynomials and you have Maclaurin polynomials. This thing we just did was a Taylor polynomial. But I don't want you to get in your head the idea that it's different than this other thing called a Maclaurin polynomial. A Taylor polynomial is just this generated polynomial that has degree n. Oh, by the way, oh shoot, here, I made a mistake. Let me fix this really fast. I shouldn't have the thing at the end, because that way I can say that this is the nth Taylor polynomial. I forgot that if I add that ... because it goes on forever, then it's not a polynomial anymore. So there it is. There is the nth Taylor polynomial for f of x centered at x equals c. There it is. So now that I fixed that. So first of all, an nth Taylor polynomial. The nth Taylor polynomial is going to be of degree n. That should make sense. It's going to be centered at x equals c. So basically, just like we did before, it's going to be centered at wherever we decide to make the center, whatever value we're plugging into the derivatives. So over here on the side, I would say this circle would represent all the Taylor polynomials that are out there. So it's all the Taylors. Now, in contrast, the Maclaurin polynomial, and the nth Maclaurin polynomial would still also be a polynomial of degree n. The only difference with the Maclaurin is that your center isn't just NEC. Your center has to be 0. So Maclaurins are just Taylor polynomials that are centered at 0. So to help illustrate that idea, those are all the Taylors. Inside here is the Maclaurins. All Maclaurin series are just Taylor series that are centered at specifically c equals 0. So it's a very small distinction. It's not even one that's going to be particularly difficult for you to get used to. So just kind of get that in your head too. So we've got these Taylors and Maclaurins. Maclaurins are just a special case that centers at 0. Taylors can be centered anywhere. In addition to that, the notation we use to describe both of these things, the nth Taylor polynomial or the nth Maclaurin, oftentimes we'll describe both of them, oops, that's an R, would be p sub n of x, and that could be true for either one. The center wouldn't be relevant, that would be just the name that we call them. We say p sub n of x, that's the nth degree Taylor polynomial, or the nth Taylor polynomial, or the nth Maclaurin polynomial. So either way is perfectly fine. So having said that, that's a ton of stuff, just kind of building up the idea. Again, I'm betting and I'm hoping probably that you sped this up just a little bit, because again, I think it's pretty repetitive. But again, all this investment is going to be to make the process easy. Now you have a good sense of where all these parts are coming from. So with that in mind, we're going to actually be able to construct pretty quickly, because the important result of all of this is that now we have what I'll call a general term for this Taylor or Maclaurin polynomial. So our goal is going to be, oops, that's ugly. Our goal is going to be using this to our advantage and working it out as quickly as we can. So having said that, I'm going to take a momentary break just because that's been a lot of talking and narrating through here. When I come back, we'll do a couple examples and they will go infinitely faster than the derivation and introductory stuff that we just did. So stay tuned. Actually, it's just going to continue for you, so whatever. Okay, enough build up. Let's actually look at some real examples here and show you the construction of a Taylor polynomial and some valuable things about them. So to start things off, I'm going to begin by asking the most basic task, and with this very simple function as well, sine of x. That task says to write p sub 7 of x, also known as the 7th Maclaurin polynomial of f of x equals sine of x. So having said that, there are a couple things here that are necessary to interpret before we jump in. First and foremost, the 7th Maclaurin polynomial says that it needs to be degree 7, which means we've got to go up to the 7th degree. So we'll have a 0 degree constant and then 1st through 7th degrees. Second, because it says Maclaurin, that means it's going to be centered at x equals 0, meaning instead of plugging in x equals c or some other number, we're going to be plugging in x equals 0 every single time. So we'll be evaluating derivatives at 0 and multiplying by x minus 0 to a certain power. So keep that in mind. That's kind of the beginning step. Now, from here, we want to generate the entire polynomial and we want to go out to degree 7. So here's my recommendation. I'm not going to write out a formal plan this way. I'm just going to narrate what it is that I do. So first and foremost, the first thing I'm going to do is I'm going to write out f of x equals sine of x. And then from here, what I'm going to do is I'm just going to differentiate this function until I get to the 7th degree term. So that means first I have f of x. F prime of x is the derivative of sine, which is cosine of x. Next, f double prime of x is going to be the derivative of cosine, which is negative sine. Then I'll do the third derivative. At this point, you've kind of got the idea of the pattern. I probably don't need to go as many degrees as I said, but I'll stick with it for now. We'll have f triple prime of x is negative cosine of x. The fourth derivative is going to be positive sine of x. And then at this point, you'll notice, hey, wait, it's just come back to the original pattern. In fact, it is. The derivative is as periodic and cyclical, maybe it's cyclical is the word I'm looking for, as the original, or as the functions themselves are. So we're down to the 6th derivative. Gosh darn it, this is taking up all my space here. But we're almost there. Again, usually ask a few smaller terms, but we'll stick around with this. I'll be faithful to the problem I wrote. And then last but not least, we want the 7th derivative, because that allows us to get to the 7th degree. So there it is. There's our first step. We just took the derivative of sine a bunch of times. We just kept differentiating all the way down. And that is your first step. Differentiate the function as far as you need it to go. So obviously, if there are patterns, in this case, you can develop a pattern pretty quickly. That's great. But if there's not, then you can't. So keep that in mind. The next thing we're going to do is we're going to evaluate the derivative in each of these situations at that x value where we're centered. So we're going to, in this case, plug in x equals 0 for every single one. So in a sense, it's like every single time I'm going to plug in x equals 0. Now, having said that, as I write this out, I realize, boy, I'm not enjoying writing this at all. This isn't fun for me to do. So as a pointer, you can, of course, plug in 0 just like that. You don't need to put the x equals 0. But then from here, something I want you to do, and this is something I've been bad about in the past, so I'm trying to be better this year, even if I'm having to teach you from my home, is basically don't write equals at this point. I just want you to draw an arrow. So in this case, sine of 0 is 0. Cosine of 0 is 1. Negative sine of 0 is 0. Negative cosine of 0 is negative 1. Negative sign, well, at this point you can figure out the signs are all 0. That's kind of nice. So it looks like we're only going to have odd derivatives that show up in here, or odd degree terms. And then next, cosine of 0 is 1. And lastly, negative cosine of 0 is negative 1. So there we go. So now, we've got the values of those derivatives at each point. If you're wondering why that's useful, keep in mind what we're really finding right now are these pieces. It's these little guys that we're finding right now so we can generate those coefficients. Having said that, though, now that we've calculated the value of those specific derivatives, we need to divide by the factorial. And that's why I wanted you to use this arrow, is because I don't want you to have what's called a linkage error, saying that this sine value is equal to something over a particular factorial, because it wouldn't be. We're putting the factorials in afterwards as a method to adjust our coefficients so that they match perfectly for the derivative. In a sense, that's the adjustment to take care of the power rule every time we differentiate and match up another term. So in this case, now that I've got it, I'm going to divide by 0 factorial. I mean, truthfully, the 0 ones you don't have to, but I'm just going to do it for simplicity. Divide by 1 factorial, by 2 factorial, by 3 factorial, by 4 factorial, by 5 factorial, by 6 factorial, by 7 factorial. So those are going to be our coefficients. Having said that, though, of course, we want to figure out what those numbers actually are. The zeros are pretty easy. They're just going to be 0. That's nice. The other ones, though, 1 over 1 is 1. Negative 1 over 3 factorial is negative 1 over 3 times 2 times 1, which is negative 1/6. Of course, you don't have to simplify factorial. You could leave it as 3 factorial, but again, I'm going to be pretty good about it. 1 over 5 factorial, 5 times 4 times 3 factorial is going to be 20 times 6, or 120. And then the last one is 1 over 7 factorial. That's 720 times 7, which I believe is 5040. Let me make sure. It is. So this one will give us negative 1 over 5040. Again, if you don't want to memorize those values, if you don't know what they are, you don't have to calculate them. Just write 7 factorial. It's probably safer anyway. So there's our stuff. Now, having done that, let me point out the next step is we now need to turn it into a polynomial. We have a series of coefficients here, but we have no polynomial until we have x to the power stuff. So keep in mind, because of the fact that we centered at x equals 0, that means all of our x factors are going to be x minus 0 to the n power. But keep in mind, x minus 0 to the n power is the same thing as just x to the n power. So really, this is just going to be 1x and negative 1/6 x cubed, 1/120th of x to the 5th, negative 1/50/40th of x to the 7th. Those are now going to be the terms of our polynomial. Having said that, though, that was enough. We could have just generated them off to the side. So what I'm going to do is I'm going to finish this up. I'm going to say over here that p sub 7 of x is equal to x minus 1/6 x to the 3rd plus 1 over 120 x to the 5th minus 1 over 50/40 x to the 7th. And this is that polynomial that we were looking for. In particular, in this case, this is the 7th Maclaurin polynomial of f of x equals sine of x. So there it is. We found our polynomial. That is the answer. So we've done it. Good job. Give us gold stars. That's not a gold star. I'm trying to find this. Oh, there it is. Gold star. It's so gold I can't even see it. There we go. Okay, having said all that, let me point out one other little thing here that might be something that's worth pointing out. This is not equal to sine of x. So as a heads up, you cannot say that sine of x is equal to this thing that we constructed. Come on, help me out, computer, sometimes. There we go. So this statement, as written right here, this is an incorrect statement. Sine of x does not equal that thing. In fact, if we wanted to show it on there, I can actually demonstrate that really quickly. What we just graphed was, let's see, are we doing 2n plus 1? We graphed this, which, yeah, it looks like sine of x, but if we zoom out, it's clearly not the same thing. Sine of x looks like that. So in order to distinguish those two things, you can't say this. You could say plus dot 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 and then add what's called the general term over here. That would be one possibility, but for right now we don't have general terms. We haven't really figured out exactly what that is. So instead, let me point out that if you want to write this statement correctly, you don't say that sine of x equals that. All you say is sine of x is approximately equal to that. Obviously, that wasn't the question asked here, but that's exactly what we came up with. We came up with something that does a good job of approximating sine of x. Obviously, from looking at that picture on Desmos, there are places where it's a better approximation than others. Specifically, you probably want to be here more than you want to be over here. But at the same time, the idea matches really nicely. So there is our first constructed Maclaurin polynomial. It was centered at 0. Had it been centered somewhere else, it would have changed the process. But since we haven't seen that yet, I'm going to demo that in the next problem. For now, though, first full example in the books. Second example, following the same basic pattern, though. In this case, we're asked to write the first 6 non-zero terms of the Taylor polynomial for g of x equals e to the 3x minus 3, centered at x equals 1. So we're going to follow the same basic process we did before. In this case, though, we're going to be doing it for this exponential function e to the 3x minus 3. And in this case, it's going to be centered specifically at x equals 1. So in this case, it can't be a Maclaurin. Maclaurins are centered at 0. This is going to have to be a Taylor, which it tells us in the problem, but same deal. Just like before, though, to kick things off, I'm going to write out the function and its derivatives. And I like to organize vertically. I mean, your mileage may vary. This is my favorite way. So g of x is e to the 3x minus 3. Now, we got to differentiate a couple times here to wrap this thing up. So let's think here. If we differentiate e to some power, the derivative will be e to some power, but then the chain rule requires we multiply by the derivative of that power. And the derivative of the line 3x minus 3 is just 3. So g prime of x is going to be 3e to the 3x minus 3. G double prime of x is going to bring an extra 3 down. We're just going to keep doing the chain rule over and over again, which means this will be 9e to the 3x minus 3. G triple prime. Something fun about saying triple prime. 27e to the 3x minus 3. The fourth derivative of g of x is going to be 81e to the 3x minus 3. Jesus, is something. Is that really how far I was going? Oh, I wrote fifth. Okay, well, I'll keep going. I can do this. The fifth derivative is going to be 3 times 81. That's 240 plus 3, so 243 e to the 3x minus 3. You can see this doesn't feel right. You know what? Let's do this. I'm not going to write the first 6. I'm good. Write the first 5. What was I thinking when I put 6 up there? It's not even what I have in my practice problems, in my like practice version of the notes. Go figure. Okay, so there it is. So there's where we've started. Just like before, we've written out the derivative. We have all the derivatives that we're going to need for these 5 terms. And again, you're not allowed to just change the problem on the AP exam, but I have that power right now. I was going to say no one can prove that I changed it, but literally you can just rewind this video and prove it, so I'm not going to say that. So instead, let's go and start evaluating. So since we're centered at x equals 1, that means we need to plug in a bunch of 1s. So I'm going to evaluate this at x equals 1. I'm going to evaluate this at x equals 1. I'm going to evaluate this at x equals 1. And just like last time, I'm kind of getting frustrated and tired of the tedium of writing evaluate at x equals 1, but this time I made it through them all. So again, be you. If you want to just write the 1, that's fine too. Also keep in mind from the previous example, I said let's not put equal sign, let's put arrows. That will save us from any linkage errors that we might accidentally run into. Now that we have it, our job is just to evaluate it, just like we did before. So if we do e to the 3 times 1 minus 3, that's e to the 3 minus 3, which is e to the 0, which is just equal to 1. So I'll go e to the 0, and then I'll put in 1. On the next one, we'll have 3 e to the 0, which is just going to be 3. On the next one, we'll have 9 e to the 0, which is 9. And at this point, 27 e to the 0 is 27. You figured out it's just the coefficient in front. It is. It is indeed. So we get those as our values. Now, last but not least, remember, we can't finish right there. Just like before, we're going to divide by the appropriate factorials. So 0 factorial, 1 factorial, 2 factorial, 3 factorial. As I do this, you might wonder, why do I put the 0 factorial and the 1 factorial in there? And the answer is one, completion. Like I don't want to leave out some part of it. Like I'm kind of attentive or kind of compulsive that way. But the other reason, the bigger reason, is simply that I don't want you to forget to put the factorials. So I just start from the beginning, and every single time I write those factorials in there. I make it a factorial every single time. Where does this leave us? Our coefficients are 1, 3, 9 halves. Ooh, 27 over 6. That's going to divide by 3 on top and bottom. I think 9 over 2. Oh, interesting. It's 9 over 2 again. This one will be 81 over 24. If we divide by 3, I think we get 27 over 8. Yeah, that right? And then this last one, do I know what this simplifies to? I can probably figure it out. Did I even write it in my work? I guess I have it somewhere, but I don't know. Divide by 3 again, I think. That'd be 81 over 40. Yeah, there we go. 81 over 40. So there it is. So we now have our coefficients. Obviously, some took some work to get there. Now that we have our coefficients, we can finally write out our polynomial. So according to the work that we just did, our polynomial is going to be equal to 1 plus 3. And now here's that problem I'm going to run into. I'm out of space. So space, the final frontier. I'm just going to make this a little bit smaller. I should have done like 2 columns or something. Yeah, whatever, we'll be fine. So right down here, I'm going to write it all out. So we have 1 plus 3. Now be careful. We can't just write x this time because this was centered at x equals 1. It's not a Maclaurin like the previous problem. So instead of writing just x, we have to write 3 times the quantity x minus 1. That way it centers at the right spot so that if we plug in 1, we get the right values. After that, we'll have 9 halves times x minus 1 squared, then plus 9 halves again, x minus 1 cubed, plus 27 over 8, x minus 1 to the 4th. Yeah, why did I want us to do an extra term? Jeez Louise. X minus 1 to the 5th, and there are the first 5 non-zero. Oh, geez. Why didn't you stop me? It only wanted 5 non-zero terms. 1, 2, 3, 4, 5. I could have saved myself 1 extra point, 1 extra calculation. So yeah, I didn't need that one at all. So there are our 5 terms. Again, you don't have to simplify things. That is the answer that we were looking for. So good job. Nice victory on our part to end up with that piece. Now, having said that, just like before, I'll put that up there as my answer now that I have it. Let me point out that, again, if you wanted to name this, for one thing, you could name this very thing. Since it turned out to be the 4th degree polynomial, you could call this p sub 4 of x. That would be perfectly acceptable. In addition, if you wanted to, you could say e to the 3x minus 3 is approximately equal to this thing. And that would be a perfectly appropriate thing. It's definitely not equal to it, because it would only be equal theoretically if we're able to go to an infinite number of terms. And believe me, this is tedious enough. You do not want to have to write an infinite number of terms. Just not a good time. So there it is. There's us generating another one. In this case, we generated a Taylor rather than the Maclaurin we did before. So there is the big idea. We've now generated Taylors and Maclaurins. That brings us to the third example, which truthfully, looking at this stuff, wow, in 16 minutes, and like half the time as before, I've done 2 huge examples, whereas before I just kind of introed the topic. Whatever. So from here, the next one, the table below gives us values of f and its first 3 derivatives. Approximate f of 4. So this is now where we finally get to really see why it is that we keep talking about these values. So we've got these approximations. We keep saying it's approximately equal to something. Well, what are we approximating? Well, for now, for up to this point, we've thought of it as approximating the entire function. But the truth is, what we're really doing is we're approximating particular values. We're generating a polynomial that we can plug numbers into and generate good approximations of some function value that might otherwise be difficult for us to calculate. So in a sense, plugging into polynomials is easy. Plugging into transcendental functions or weird functions is not always so. So in this case, what we want is we want to approximate the value of this function f of x at x equals 4, but all we have is information about what's happening at x equals 2 and the derivatives around x equals 2 as well. So in generating this one, we could think of it in kind of the same way. We could think of it as generating a list of function values and derivatives, but in this case, I think it's going to be easier just to think about it in the full form that we did before. Well, actually, I'll keep the pattern the same. So what we're going to do, we'll start with f of x. But here's the thing, we don't know what f of x is, so instead let's just do this. We're going to be plugging in whatever our x value is that we have. In this case, it's x equals 2. So rather than start with just f of x, I'm going to start with f of 2. And according to the table, f of 2 is equal to 5. Oh, here we go. Sorry, just like before, let's use arrows just to be safe. F of 2 is 5. Reading the table, f prime of 2 is going to be negative 3. Reading the table, f double prime of 2 is going to be 8. And reading the table one more time, this is much more reasonable. F triple prime of 2 is going to be negative 42. So what have we done? We've accomplished and successfully found the value of the function at each of those points and its derivatives at that point, x equals 2. And again, if you're wondering why did we choose 2 when we're trying to find f of 4, the reason is 2 gives us the opportunity to write a Taylor polynomial that's centered at 2. Like we don't have the derivatives for 4. We're trying to approximate 4, so we're going to write a polynomial that's centered at 2 and then plug in 4 to figure out what the approximation would be. So having done this, we've got our values of f. So we've kind of accomplished the beginning of this. Now we need to divide by the factorials. 0, 1, 2 factorial, 3 factorial. So setting these equal, we get 5. We get negative 3. We get 8 over 2, which is 4. And negative 42 over 6, which is negative 7. So interestingly enough, from the terms and the information we have, it looks like we have an alternating polynomial. Not that it matters for now, but it is what it is. So given that, we were supposed to approximate f of x. Right now what we have is 5 minus 3 times the quantity x minus 2. Again, we're centering it because it's centered at 2. Plus 4 x minus 2 to the second minus 7 x minus 2 to the third. Now again, keep in mind, it's not that we don't have factorials here. We definitely do. We've just simplified. I designed this problem so that they cleaned up really nicely. So this, many people would say, well, what is this? This is p sub 3 of x. And that's true, but I don't think that's a valuable way to look at it in this particular problem. Instead, I would encourage you to think of it this way. What we have is an approximation of this function f of x that we don't know very much about. In fact, I'm just going to change that color so that it stands out a little bit more. Like, we don't know much about f of x. We just know a few derivatives and a function value at a particular point. So that is our approximation of f of x. The reason I bring that up is we want to approximate f of 4. So let's just do... Oh, wait a second. Watch this. Watch this. Oh, look at this. Oh, yeah. Nobody to yell at me for copying things that they have to write down. Oh, this is the only positive silver lining that I can find in this. Nobody yells at me for this. So what I'm going to do, I'm going to plug in 4 the x value. So I want to plug in 4, because we're trying to figure out what's f of 4. Well, f of 4 is going to be what happens if we plug into the polynomial. It's going to be a good approximation, at least, going out a few terms. So having done that, what does that leave us? 5 minus 3 times 2, so minus 6, plus 4 times 2 squared. That's 4 times 4 is 16. I should be more careful since I can't check this work. I wrote this problem new. This will be 2 to the third is 8 times 7 is 56. So according to this information that we have, using the second, or the Taylor polynomial centered at x equals 2, we get -1 minus 40. Oh, are you telling me I was that close to -42? Oh, man, if I'd made that first value 4. Oh, well, in any event, what we just did was we approximated f of 4. So again, the real value for us, like one of the big motivating factors, there's a lot of reasons why Taylor polynomials will be useful, and we'll expand on some of them tomorrow or in the next lesson. But if you're looking for one really valuable reason that these are great, look how easy it is to approximate. I mean, try to approximate with a function we don't know anything about except for a couple derivatives, not going to get too far. This does a nice job. So what do? We wrote the Taylor polynomial, in this case centered at 2, and then we plugged in the x value we were trying to approximate f of x at. And we got our value, which was painfully close to 42, or -42 in this case. But, oh well, we got our thing. Okay, so having said that, that completes the examples of this lesson. I did promise to try it at the end, and I'm going to get you there. The only thing I wanted to do, though, first was I just wanted to point out a couple facts that I want you to take. Like, these are kind of, I was going to say axioms. They're more or less theorems. I'm not going to prove them for you. Guidelines? Let's call them guidelines. They're guidelines to kind of guide, there it is, to guide you as you think about Taylor polynomials and Maclaurin polynomials for the first time. So these are facts about these polynomials, and I think you've seen some of them, so you might already have some graphical intuition about them, but just let's put them out there just to be safe. So basically the first fact says, an approximation of f of x using p sub n of x is more accurate closer to x equals c. So in this case, what we're trying to say is that if your approximation is closer to the center, then you're going to get a better read on the problem. So now, in this case, this is hard for me to demonstrate for you. I think one of the best ways is just to indicate this. So I'm going to hold off on putting any other information in there. Let me just point out this. If I look at this curve, this is centered at x equals 0. This is a Maclaurin. There's something weird going on in there. But it's because it's trying to... there it is. Okay, so it's centered right there. So if we look at the points here, you can't even tell the difference between the sine curve and the Taylor polynomial, or the Maclaurin. So the idea is if you're close to that center at 0, your approximation is really good. The further out you get, the worse your approximation is, because that's where the ends, the tails of this Taylor series are going to grow and grow without bound, because of course it's a polynomial. It's going to have some sort of end behavior where all those things are happening. So in this particular case, what it's saying is your approximation is closer to this, is better closer to the center. So let's see. Yeah, this is good enough. I think that's a good enough explanation. I have a bunch of stuff in here, like looking at my notes, I'm like, well, why did I approximate it? I think you're okay. I think that's a fair enough thing to say visually. The second statement I want to talk about says, the second fact, is that an approximation of f of x is more accurate using p sub n of x than p sub n minus 1 of x. And this second one, excuse me, I'm talking too much. This second fact is, I think, a good candidate to kind of simplify down. More terms equals more accuracy. So the idea here is, if you want to get a more accurate estimate of f of x using its nth degree Taylor polynomial, you can improve that accuracy by adding more terms. And once again, just like the first one, the truth is we already saw this in action. Remember, what we did at the very beginning, or what I did was I tricked you or I showed you that you could slowly stitch more and more things. What's happening here on the left as t increases by 1 each time is we're increasing the number of terms in this polynomial, which means they're slowly making it more and more accurate. It's covering and converging to more of this function. So the idea is that, like, if you add more terms, you get a more accurate approximation. I mean, look at that. Like, all the way out to -20. How many periods is that? 1, 2, 3, 4. Like 8 periods in both directions are all accurate now just because we added more terms. So that's what that second one is saying. If you add more terms, you get a better approximation than you would otherwise. And again, as I mentioned in my notes, I've done some stuff like I've gone through and calculated sine of x approximations using that polynomial from before, but I'd rather not. I felt like I lost that ability to do extra explanation because I took so long deriving the entire Taylor idea. So having said that, like I was trying to write one that looks so unparalleled to be close. Oh, here we go. Closer to center. Yeah, see, I like these tagline styles. Closer to center equals closer to actual value. Haha, look at that. Proud of that result. So there we go. So basically those are the two facts. Like I want them to just kind of settle in. I think you'll start to come to these conclusions, but sometimes, especially with the approximation one, I forget to even have you do the approximation, just kind of take it as a given that it's there. That's why I created that new problem and why I wanted to talk about this a little bit more. But again, I think you have some good visual intuition about these that can help support you as you work your way through. So having said that, the last thing I'm going to do is give you the try it. So let me just take a second and I'll turn it on and open it up for you, and you can take a look and try some problems on your own. Okay, as I said, here is that collection of 3 try-its. They kind of mimic the same structures of the questions that you saw earlier in the examples. I'm going to leave the lesson right there. I'm going to let this be the final bit. If we were in class, I would probably have you work through these and then bring up your answers to me. You'll notice I didn't include a QR code for these of any kind or some sort of Google form. The reason is I really just want you to focus on doing these, and having to format a question or shorten a question to make it easy for a Google form to work just didn't feel like the right choice for this particular topic. So instead, this will definitely be one where you just check your answer on the try-it solutions and make sure you're in good shape. Having said all that, thank you again for watching. Hopefully this was a helpful coverage. I know it went a little slow at the beginning. I apologize. I just like to make sure that I give you a really detailed introduction. I like to really front load before I dig in and just start doing stuff so that you have some understanding of where things come from and how these things are connected to what's there. So again, thank you for watching. It's always a pleasure to teach you, whether you're in front of me or not, or I'm just pretending that you're there by pressing buttons like that the whole time. Yeah, that's an accurate estimate. Sometimes class feels that way, like you try to get people's attention back. But in any event, thank you, and hope you're healthy and well, and I hope this was a strong and informative introduction to the topic of Taylor and Maclaurin polynomials. Have a good night.